Hello guys, how are you today? So today I'll be explaining AP Chemistry Chapter 2. And of course, again, as I did for Chapter 1, I'm gonna be dividing them into sections. So we first start with the first section. So the first section really just talks about the periodic table. This is literally all it talks about. So I'm just gonna be stating some information. I'm not gonna be writing anything unless it's like extra necessary for um, 2.1. So let us start in all scenarios. Now, the modern periodic table, which is the periodic table we have in front of us, or like in front of me, is organized based on the atomic numbers. That means based on how many protons there is in each element, this is how they are organized. With 1 being the smallest number of protons and 118 being the biggest number of electrons so far that have been discovered. Now, what do we notice in the periodic table? In the periodic table, we notice that we have a couple of columns. These are called columns. And we have a couple of rows. These are called rows. Now, in chemistry, we don't say rows and columns. We say periods instead of rows. And instead of columns, what do we say? We say groups. Now, we have exactly how many columns and exactly how many groups. First of all, we have 18 columns, right? Columns is a group. And we have 7 rows. Rows is a period. Now, what is something essential we need to know? We need to know is that atoms in the same column, so atoms in the same column have similar configurations. For example, as an example, let's take any column. Let's take this column, for example. And let us take Na and K and let us do their configuration. Na, 11, K, 19. The configuration of Na11 is what? Is neon 3s1, whereas K19 it's argon 4s1. So what do we notice? They have similar configurations. In which sense? In the sense that they end with exactly the same thing. The only thing that differs is their core electrons. So the core electrons, of course, are the number of electrons that the noble gas behind it has. So for sodium, neon is the core electrons, and argon is the core electrons for potassium. And what do we notice? We notice that they have similar configurations in that they both end with S1. Okay, so this is something very important we need to know about columns, is that atoms in the same column have similar configurations, and that atoms in the same period have similar, or actually not similar, they have the same energy level denoted by N. So for example, let's take any 2 elements that are in the same period. For example, we take sodium and magnesium. I think by now you guys already know that sodium is my favorite element for some reason. So sodium, what is its electronic configuration? It is very simply neon 3s1. And magnesium, its electric configuration is neon 3s2. So as you can see, they both have what? They both have the same electronic configuration. So very simply, in the same atoms in the same period have the same energy level. Perfect. Now, what is something very important that we've learned many times over the years in science? We learned many times over the years in science that as we go down the periodic table, each group has the same chemical properties. So we can add that down a group, chemical behaviors and reactivity is similar. So down a group, chemical behaviors and reactivity is similar. Now, every time we move from row to row, right? Let's say you ended at neon and then you moved to sodium, what's gonna happen? There is gonna be what? There's gonna be an increase of energy level. Perfect. But another thing we can notice is that whenever you go from an old row to a new row, you always end up where you always end up in the first group. And the first group has a charge of what? Of 1 plus or plus 1. The second group has a charge of 2 plus. The third group, or let's say the 13th group, has a charge of 3 plus. The 14th group has a charge of 4 plus or minus. The 15th group is 3 minus, 16th is 2 minus, and then 17th is 1 minus, and 18th is 0. So what do we deduce from this? These, the 1 plus, 2 plus, 3 plus, 4 plus, minus, 3 minus, 2 minus, 1 minus, and 0, well, 0 is not actually, but these, okay, they are known as what? They are known as valence electrons, or electrons on the last outer shell. Why are these important? Because these are the electrons that react with all other elements. So for example, Na will be positive. Cl is going to be negative. The only two things between Na and Cl that will react together are the positive and the negative, which make them attract and form NaCl. Okay, so this is very much what I need to say. Oh yeah, other than the different types of blocks, we have something very important in chemistry. We have some things known as S block, D block, P block, and F block. This is something very, very vital to memorize. So the first two groups, okay, group 1 and group 2, these are known as what? These are known as the S blocks. Now what comes after S? It's S, P, D, F. So then comes the P blocks. The P blocks are from group 13 all the way until group 18. So these are what? These are the P blocks. Now let me change the color. Now, what comes after P block? We have after P block the D blocks. The D blocks are from group 3 all the way till group 12. So all of this in red is what? Is a D block. And that leaves us last but not least with what? With these over here. The lanthanides and actinides, they are called what? They are called the F block. Okay, so these you're supposed to have them memorized. They're very, very important to have them memorized. And just like that, we finished 2.1. Let us now move on to 2.2. Now, what is the first concept we talk about in 2.2? The very first thing we talk about in 2.2 is what is the atomic radius. The atomic radius, abbreviated as A dot R. To not waste any time, we'll abbreviate it as AR. The atomic radius is what? Is an estimate. It's not an exact value because you cannot measure the value of an electron. It's so tiny. There's no rule that's that small to measure the exact value in between and this and this. Instead, it's what? It's an estimate of the distance between the nucleus of an atom and its outermost electron. Perfect. So the atomic radius, AR, is an estimate of the distance between the nucleus of an atom and its outermost electron. Now, how do scientists actually calculate it? They will have two identical atoms. So because they're identical, I'm going to copy this. Copy, move it, then paste. Yeah, so they're two identical atoms next to each other, side by side. And what happens? They will put their nucleus, they will draw their nucleus. We have a nucleus over here and a nucleus over here. So how exactly do scientists calculate this value? Is that they take two identical atoms and they're bonded together, right? And then they take the distance from one nucleus to the other nucleus. I don't know why this disappeared. Yeah, so they take the distance from one nucleus to another nucleus. And this distance, let us call it distance small d. Now, this is the distance between one nucleus and the other nucleus, but we are looking for the radius. So very simply, the radius is going to be what? Half of the distance. Okay, so this is how scientists calculate the value of the atomic radius. Now, we move on to a very, very, very important concept, which is how does moving across the periodic table affect the atomic radius. Now, atomic radius down a group. The first thing we'll talk about is the atomic radius down a group. Down a group means going down like this. Let's take two examples. You can go back up to the periodic table over here. Let's take two examples down a group, which is sodium and potassium, my two favorite examples. Yalla. Sodium Na11, potassium K19. This is going down a group. Now, how does the atomic radius differ down a group? We should know first of all that the atomic radius is affected by a couple of things. What are these couple of things? The first thing is the nuclear charge. After the nuclear charge, we have something called the shielding effect. After the shielding effect, we have something called the energy level, and the very, very, very last thing, of course, energy level and sub-level. We can write them together. And then the very, very, very last thing we resort to, if needed, is the box or the orbital method. It's called the orbital method, but I like to call it the box method. Now, regarding Na and K, Na11, K19, let's write first of all their configuration. This is gonna be neon 3s1, and this is what? This is argon 4s1. 4s1, yeah. Now, what can we say first of all regarding the nuclear charge? The nuclear charge of sodium is less than that of potassium. Second of all, the shielding, we'll look at the core electrons. Which one has a greater core electron? Definitely potassium has a greater core electron, so it has a greater shielding than that of sodium. Now, energy and sub-level. So sub-level is the same. I'm just gonna write same over here next to sub-level. Whereas the energy level, I think I'm gonna erase this. Whereas the energy level of, which is N, of sodium is less than that of potassium. Now, finally, this is, like everything is clear, so we don't need to use the box orbital thing. So what can we infer from this? Very simply, let us draw and think of it logically together. If the let's first of all draw the nucleuses. First of all, the nucleus of sodium is smaller than that of potassium because it has 11 protons, whereas the potassium has 19 protons. So this is done regarding the nuclear charge. Now, we move on to what? We move on to the shielding effect. Sodium has the shielding effect of Ne. That means there's 2 orbitals around it, or 2 like rounds around it. Whereas potassium has the shielding effect of what? The shielding effect of argon. So it has 1, 2, and 3 shields around it. Now, last but not least, requiring the energy level in where the extra electron is found. This is the 3rd energy level, whereas for potassium, it's the 4th one. So as you can see, we know that the valence electron, or the electron we're dealing with, is always on the last shell, and then the protons are on the inside, or the nucleus, sorry. And now, as you can see, definitely what happens, potassium K has a greater atomic radius. So from this, we can deduce what? We can deduce that as we go down a group, atomic radius is gonna increase. Okay, this is very, very important. Perfect. Now that we finished with down a group, we'll move on to the next idea, which is the atomic radius across a period. So I'm not gonna keep on going back and forth to see the periodic table. I have it in front of me. You guys are also supposed to have it in front of you. So we can take the example of sodium Na11 and magnesium Mg12. So these are what they are across a period. Perfect. Now, what again are the effects that will affect the atomic radius, or what are the things that affect the atomic radius? We have, first of all, the nuclear charge. Second of all, we have what? We have the shielding effect. Third of all, we have the energy level N. Okay, fourth, like you can include sub-level as well. And then the last thing we resort to is what? Is the box or the orbital configuration. Perfect. Now let us do it. First of all, sodium, we said it's neon 3s1, and then magnesium, it is what? It is neon 3s2. So first thing we notice is that magnesium has a higher nuclear charge than sodium, which has a shielding effect, higher shielding effect. They both have the same shielding effect because they both have the same core electron. Now, energy level and sublevel in this scenario, because as you can see, going across the period, you'll see that the sublevel increases, whereas the energy level stays the same. So the energy level in this scenario and the sublevel are the same. So what do we do in this scenario? If we have only nuclear charge to help us, in this scenario, we open the box orbitals. Very, very important concept. So let's take it as Na and Mg. Let us draw. This is 1s2, 2s2, 2p6, 3s1. And this one is 1s2, 2s2, 2p6, 3s2. Perfect. Now let us draw the box configuration. One box here, one box here, one big box here divided into 3, and then one box for the s. And same here, one box here, one box here, one big box divided into 3 orbitals, and then one for the s. Now we start putting the electrons. We start always one up, one down. Here, exactly same thing, one up, one down. Here we start by filling one up, one up, one up by Hund's rule. One down, one down, one down. And here, one up. Whereas here it's one up, one down. One up, one down. One up, one up, one up, one down, one down, one down. One up and one down. So now there comes a very important concept we are supposed to know, which is what? Which is the electron to electron repulsions. We know that when two electrons come together and they are of opposite spin, they are said to be what? They are said to be paired. Now, two paired electrons will create a repulsion, and this repulsion will push away any unbound or any unpaired electron. Perfect. So, this paired electron pushes away using the repulsion. Then this is also a paired one. It will push away as well. Also a paired one. And a paired one. And a paired one. And all of these will have a force effect on what? A force effect on this single unpaired, on the single unpaired electron. And this will result in what? This will result in a larger, not a larger. Yeah, and sorry, my bad. In a larger repulsive force which increases atomic radius. Now, let us compare this to the magnesium. Magnesium has this repulsion, and 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 this repulsion. So they're all working together towards where? Towards this empty orbital that we have over here. Or like we don't have an orbital, we don't have anything. And they're all going like that. So because of this, there is less repulsive force on valence electrons. Okay, so then what happens? So then the atomic radius will decrease. So what do we need to know? We need to know that as we go across the group, so did I say across the group? I meant to say across the period. As we go across the period, the atomic radius decreases. And if this were to come in the written part, you are supposed to write, although nuclear charge increases, because as nuclear charge increases, logically speaking, it's supposed to increase the atomic radius. But in this scenario, because we're moving across a period, you can say, although the nuclear charge increases, we have what? We have same shielding effect, same energy level. So the forces of magnesium are less repulsive than those of the electron-to-electron repulsion of sodium, and thus we can deduce what? We can deduce that sodium will have a larger atomic radius than magnesium. Perfect. Now we were talking about what? We were talking about atomic radius. Let us move on to something called ionic radius. Now, what you need to know is that what applies to neutral atom does not apply to ions. This is something very, very, very important. So all of the rules we discussed above do not apply, not a single one of them, to the ionic radius. What do we need to know? We know that we have some atom. Let's say we have Na, Ba, O, and Cl. And they told us to do what? To label based on largest atomic, not atomic, my bad, ionic ionic radius. Perfect. So label based on the largest ionic radius. Very simply, there's a set of rules you need to know. What is the set of rules? Logically speaking, if you remove an electron, removing an electron, what will it do? It decreases the ionic radius or the atomic radius. Let's say it decreases the atomic radius. But if you add an electron, what does it do? It increases the atomic radius. So what can we say? We can say, logically speaking, that cations, because we are removing from them electrons, they will have what? They will have a smaller ionic radius. Okay? And they are smaller, what? They are smaller than their usual atoms. Whereas for anions, okay, because we're adding electrons to anions, meaning they become negatively charged, that means that anions are gonna have what? They're gonna have a larger ionic radius, and they are usually larger than their usual atoms. So now, if they told you to list from the largest ionic radius, so let's start with the largest ionic radius. What do we do? First of all, we change into ions. It becomes Na+, Ba2+, O2-, and Cl-. We said we start with the largest ionic radius, so it definitely has to be the one that has the most added electrons, which in this scenario is O2-. It has a larger atomic radius than Cl-, which has a larger atomic radius than Na+. Why? Because the more you remove electrons, the smaller the radius becomes, and then which is larger than what? Which is larger than Ba2+. Perfect. So from this, what can we say? We can say, as a general rule, that ionic radius decreases as nuclear charge increases. However, there is a sudden increase from the 14th group to the 15th group. So in general, ionic radius will decrease as the nuclear charge increases. However, there is a sudden increase from the 14th group to the 15th group. So now that we've been talking about ions, we need to discuss a very important topic, which is isoelectronic ions. Isoelectronic ions are what? They are ions containing the same number of electrons. So ions containing the same number of electrons. Let's take some examples. K+, Ca2+. These are two isoelectronic. And we can also have what? Cl- and S2-. These are also what? Isoelectronic. So if you were to do for either potassium or calcium, the electronic configuration, what would you get? You would get 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. This will go bye-bye. So for both potassium and calcium, this is the ionic configuration. Whereas for both chlorine and sulfur, is it sulfur? Yeah, and sulfur, it is what? It is 1s2, 2s2, 2p6, 3s2, 3p6. There we go. So what do we also notice? We also notice that potassium and calcium are also isoelectronic with what? With chlorine and sulfur. So as long as they have the same number of electrons, we say that they are what? They are isoelectronic. Now, we need to know that the higher the nuclear charge is, the higher the attractive forces are. Attractive force. And perfect, just like that, we finished what? We finished chapter 2 2.2. Now we'll move on to our next chapter, which is what? Which is chapter 2.3, which discusses ionization energy. So chapter 2.3 discusses what? It discusses ionization energy. How do we spell ionization energy? Let me just zoom in. It is what? It is spelled as ionization energy. What is ionization energy? It is the energy required to remove an electron from each gaseous atom or ion in a mole of atoms or ions. So ionization energy, as we will see later, is opposite to what? Is opposite to electron affinity. So ionization energy is the energy required to remove an electron, whereas electron affinity is the energy change associated with the addition of an electron. Now let us start with the ionization energy. The thing we know about ionization energy is that it is always, emphasis on the always, endothermic. And because it is always endothermic, what does it mean? This means that it requires energy. So in order to remove an electron, we require energy. So what does the first ionization energy look like? First ionization energy, I'll call it IE. The first ionization energy looks like this. You have an element X, which is a gas. You will add to it the energy in order to do what? In order to take away what? To take away an electron. So you will add energy to this element in order to remove what? In order to remove the electron, which is what? Which is E minus. So perfect. Let's move on to a new concept, which is not a new concept, sorry, to a new part, which is the factors affecting ionization energy. Factors affecting ionization energy. So what are the factors that affect ionization energy? We start with the very first factor, which is the atomic radius or atomic size. Both mean the same thing. So usually smaller atoms or atoms that have a smaller atomic radius, so let's write smaller atoms usually have electrons closer to their nucleus, right? So usually atoms that are smaller have electrons that are closer to their nucleus, right? So because of this, attraction between electrons and nucleus is greater. Thus we require a higher ionization energy in order to remove what? In order to remove the electron. This was the first condition, the atomic radius. Second condition is the shielding. Let us take a scenario in where we have an atom that has a large shielding. For example, krypton, R5S1, and argon, 4S1. Now, definitely in this scenario, Kr is the bigger core electron or has more core electrons than Ar. So what does that mean? If it has more core electrons, that means there's more things, like more electrons protecting the nucleus, right? And if there's more electrons protecting the nucleus, that means the valence electrons, what happens to them? The valence electrons, they will be at a farther distance from the nucleus. And if they are at a farther distance from the nucleus, that means they are what? They are gonna have a less attraction. So because there is a less attraction, so less attraction due to, so there's gonna be less attraction due to the greater distance between nucleus and electron. This we're talking about like if there's a greater shielding effect, okay? And due to this, the ionization required will be what? It will be less. Okay, Perfect. Now we'll move on to the third step, which is what? Which is the nuclear charge. As the nuclear charge increases, we know first of all that nuclear charge is the number of protons. So, as the nuclear charge increases, atomic radius will decrease. Why exactly is that? Because if the number of protons increase, that means there's going to be more positive charge. That means they're going to attract what? They're going to attract the electrons more. So more protons will attract the electrons more. And when they attract the electrons more, what's going to happen? They're going to pull them closer. So what happens to the atomic radius? It decreases. And thus to remove one electron will require what? Will require more energy. So thus the ionization energy will increase. Now, from this, we can now talk about ionization energy in two scenarios. If it's across a period or if it's down a group. So we said across a period, what happens to the atomic radius? We said as we go across the period, the atomic radius decreases. This we can get it from if you scroll up or if you go back in the video where we talked about atomic radius across a period. We also know that the shielding effect is literally the same. The nuclear charge increases as you go across the group. And as you go across a group as well, the energy level, which I'm just going to call it N, the energy level N, what does it do? It stays the same as well. So regarding all of this, if the atomic radius decreases, the shielding stays the same. The nuclear charge increases. So atomic radius is less, it's smaller. Nuclear charge is bigger, right? So we have more protons. The energy level is the same and the shielding effect is the same. What's going to happen? The nucleus will attract all of the electrons very, very, very strongly. Thus, if we are wanting to take away one of the electrons, we will need definitely way more energy. Now, regarding the second one, which is down a group, we said as we go down a group, atomic radius increases. This you can see from up when we were studying up. The shielding effect, it increases as well. The nuclear charge increases as well. This is two dots, increases as well. And then last but not least, the energy level increases as well. So atomic radius increases, shielding effect increases, nuclear charge increases, and the energy level increases. So what does this mean? This means, very simply, that the distance between the electron and the nucleus increases, right? Because the atomic radius increases, energy level increases, shielding effect increases. And even though the nuclear charge increases, we will need what? We'll need less energy because there's going to be less attraction between the nucleus and the electron. Now, of course, as to everything in chemistry, there's nothing in chemistry. Tell me one thing in chemistry that does not have an exception. As to everything in chemistry, it's the same in French, by the way. In grammaire, everything has exception. So think of chemistry like French. It's literally everything full of exceptions. So exceptions. Okay, what are the exceptions in this scenario? We have groups 2 and 3. And I'm going to explain why. And then groups 15 and 16. So what do we know? We know that the exception is if we move across a period from groups 2 to groups 3. So groups 2 and groups 3 in this scenario is what? Is magnesium and aluminum. And groups 15 and 16 are, for example, let us take phosphorus and sulfur. Now let us write the electronic configuration of all of them. First of all, for magnesium, it is what it is? Neon 3s2. For aluminum, it is what? It is neon 3s2 3p1. So look what happens. We said that if we go across a period, the ionization energy will increase because the force of attraction is greater. But only in the case when we move from group 2 to group 3. Why is that? Because we're adding a new subshell. So it goes from 3s2 to 3p1. So because we're adding a new subshell, what's going to happen? The atomic radius increases, and because the atomic radius increases, we will then require less energy. So this is the first exception. Why? Second exception, phosphorus and sulfur. Phosphorus is 15, so it is what? It is neon. Again, 3s2, 3p3. And sulfur is what? Sulfur is neon, 3s2, 3p4. Now, why is this different? They both have the same core electrons, meaning the same shielding effect, the same energy level, the same sublevels. What is different in this scenario? In this scenario, let's draw the box of the p's. So let's start with 3p3. So we fill in one up, one up, one up. For this one up, one up, one up, one down. Now what is the difference? Exactly, it's these. We have, first of all, 3 unpaired electrons, or what? Or a half filled orbital. And then here we have what? Here we have one pair of paired electrons and then 2 unpaired electrons. Now, what did we say? When we have a pair of electrons, they will exert electron-to-electron repulsion. This electron-to-electron repulsion of the spin pair will cause these to what? Will cause these to be moving further. So because they're moving further, because they're farther away from the nucleus, because of the repulsion of the electron-to-electron, it's gonna be easier to take them out. So it's gonna be what? Easier to take these out. Whereas these, because there's no electron-to-electron repulsion, it's gonna be what? It's gonna be harder to take them out. So these are definite, like, the exceptions. And now finally, last but not least, how can you prove all of this? Using Coulomb's law. If they ask you how do you prove all of this using Coulomb's law, you say that force is the energy required, K is a constant always, Q1 is the charge of the nucleus, Q2 is the charge of the electrons, and R squared is what? Is the distance or the radius, or let's say the atomic radius. R squared is the atomic radius squared. So this is all what? This is all first ionization energy. So now we move on to what? We move on to something called successive ionization. So definitely, removing, first of all, ionization energy is the removal of an electron from a gaseous atom. But now, successive ionization is what? Is the removal of an electron from a gaseous cation of positive 1 charge. This is maybe the secondary ionization, or let's just say a gaseous cation, okay, is more difficult than doing so to an atom. Why exactly is it more difficult? Because in a positive cation, the protons are greater than the electrons. And in this scenario, the protons are going to attract the electrons more. So the cation will attract the electrons more, will attract the valence electrons more. And due to this, the second ionization energy, or the successive, let's say successive ionization energy is what? Is greater than the ones before. Okay? Perfect. Now what do we need to know? We need to know that ionization increases while removing successive electrons, which is that successive ionization energy is greater than the ones before. Now, a scenario they will give you. They will give you a table, right? Let's say they give you a table like this. They will give you a scenario. Maybe you have 1 joule here, 2 joules here, 4 joules here, and all of a sudden you have 100 joules here. And then you have 250 joules here. And they will tell you that this is for what? This is for an element X, okay? This is the ionization of an element X, that reacts with what? That reacts with O2 minus, give us the equation that X makes with O2 minus. How do we solve this? Very simply, we start by calculating. From 1 till 2, we multiply by 2. From 2 till 4, we'll multiply by 2. So as you can see, it's constant till now. But then from 4 till 100, we're multiplying by 25. So where does the big jump happen? It happens here. So how many ionization energies is that? That is 3 ionization energies. So because there are 3 ionization energies, that means it's going to be X to the power of 3 plus. So what's going to be the compound? X2O3. Perfect. Now, finally, we finished what? We finished 2.3. We'll move on now to 2.4. We will now discuss what? We will discuss electron affinity, electronegativity, the melting point, and electrical conductivity in this section. We're going to start, first of all, number 1, with electron affinity. What is the definition of electron affinity? We said electron affinity is the opposite of ionization energy. Electron affinity is the energy change associated with the addition, not the removal, the addition of an electron to a gaseous atom or ion. And a general equation for that would be what? Would be gas, element X, in addition to an electron will give us what? Will give us X minus gas. So what do we need to know? We need to know that the greater the electron affinity is, the more negative its value. So the greater electron affinity is, the more negative its value. What do we also need to know? We need to know that across a period, electron affinity, which I'm going to label as EA, like EA sports, as we move across a period, it becomes what? It becomes more and more negative, so more and more negative. Whereas as we move down the group, what happens? It becomes less negative, right? So as we go across a period, it becomes more negative. As we go down the period, it becomes what? It becomes less negative. Now, why does it become more negative across a period? Very, very simply, across a period. Very simply, across a period, the nuclear charge increases, right? And we also said the shielding and energy is supposed to be what? Is supposed to be the same, right? This is across a period. So what happens if we add an electron? Because this is the definition of electron affinity. We add an electron. Adding an electron. So that means what? Adding an electron gets easier. Why is that? Because the atomic radius is less across a period, right? The atomic radius is less, and attraction of nucleus increases. So the nuclear charge increases, the shielding and the energy level is the same. So adding an electron gets easier because it's what? The atomic radius decreases and the attraction of the nucleus thus increases, so it's going to be easier to add an electron. So what happens? There will be what? More energy being released. So that's why it becomes what? It becomes more negative. And because more energy is being released, there will be a stronger attraction. And when there is a stronger attraction, then we can say that there is a higher electron affinity. Now let's talk about down a group. What do we know about down a group? We know that down a group, the nuclear charge increases, the shielding effect increases, the energy level N increases. Now, with all of these combined, we're going to have what? We're going to have a larger atomic radius. As we go down the group, the atomic radius increases. Due to this, it is harder to add an electron. So because it's harder to add an electron, less energy is released, okay? So then what happens to the electron affinity? The electron affinity is less. Did I say less up? So it is less what? It's less negative. Perfect. Now we move on to something that both chemistry and French have in common, which is what? Which is the exceptions. Very simply, we have two exceptions, which are from group 1 to 2, and then from group 14 to 15. Now look how this happens. In these two groups, what happened? In these two groups, there's gonna be what? There's gonna be an increase in electron affinity. So electron affinity, I don't know, I opened my bad. How do I close this? Give me a second, guys. Here we go. Okay, so electron affinity will become more positive. Now, why exactly does that happen? There's two reasons. The first reason is from group 1 to group 2. Let's choose, for example, from sodium and magnesium. Sodium Na, magnesium Mg. Sodium, write its electronic configuration 1s2. Or no, sorry. Let's write the electronic configuration. It's neon 3s1. Whereas Mg, it's neon 3s2. If we did electron affinity and we added an electron for sodium, it's gonna be what? It's gonna be 3s2 because we're adding an electron here. Whereas for magnesium, it's gonna be what? It's gonna be 3p1 because we already filled this. We need to fill a new one. Because we're adding a new subshell, the electron affinity will become more positive. Because the atomic radius will then increase. Now from 14 to 15. From 14. Let's take two examples from 14. Silicon, Si, and phosphorus, P. Silicon is neon. What's silicon? Silicon is 14. Neon, 3s2, 3p2. Sorry, my bad. And phosphorus is what? Phosphorus is gonna be neon, 3s2, 3p3. Now look what happens in this scenario. In this scenario, if we did add an electron, it will become 3p3, and here it would become 3p4. Now if you were to draw the original boxes, for 3p2 it would be 1, 1. And for 3p3 here it would be 1, 1, 1. But now we added one electron, so this becomes what? This becomes half full. Because it's half full, what's gonna happen? The attraction of the valence electron to the nucleus is gonna be stronger, right? And then we add one of opposite spin. So what's gonna happen now? There's gonna be repulsion for these two. So the atomic radius will increase, and then it's gonna be easier to take them out. So the electron affinity will become what? It will become more positive, very simply. So now, where did we reach? We reached to the point of melting points. Okay, so let us deal with the melting points. For example, melting points of period 2. Let's see what we have. We start with a metal, and then it gradually increases to another metal. And then it increases to another metal. And then it increases to the maximum to what? To a giant molecular or a giant covalent. Giant molecular or covalent. Okay, giant molecular or giant covalent. Then it decreases directly to what? To molecular or covalent. And then the rest are the same, molecular or covalent. So what can we infer from this? Or no, it doesn't increase that much, by the way. It increases gradually like this. Let me plot. Okay, so it will decrease gradually like this. Molecular, molecular, and then finally molecular. Now, why does it increase from metals and then it decreases for the molecular? First thing, because metals are what? Metals have metallic bonds, which are really strong bonds, so they require a lot of energy to break them, and to get a lot of energy we need a lot of heat. Whereas molecular have very weak bonds, right? And because of the weak bonds, they don't need too much energy in order to break them. Now this leaves us for the giant molecular, which has the most amount or the most strongest bonds. Most strongest bonds. Perfect. Now it's the same for all other groups. When it starts with metal, then metal, then metal, and it increases to giant molecular or covalent, then it decreases regarding the molecular. Now we finished the melting point. Now we will what? Reach to electrical conductivity, EC. Electrical conductivity. So look how the electrical conductivity is in a group. Just let's take any group as an example. We start off with a metal, then it increases to another metal, then it increases to another metal, right? And then it decreases gradually to what? To the covalent bond, the giant covalent. Of course, exclusion of graphite. Graphite is an exclusion in carbon, but in general, usually they don't conduct. So, to the giant covalent, so Si, and then, I wrote Si, my bad. Giant covalent. Then we have covalent, and then etc. so on and so forth, we have covalent. So why exactly is this? We know that electrical conductivity only occurs with delocalized electrons. So it's not going to make sense for giant covalent and covalent, which don't have any delocalized electrons, for them to be able to do what? For them to be able to conduct electricity. Because electricity will pass through the delocalized electrons and it will be able to pass. But these delocalized electrons are found only in the metals. So this is how it looks for majority of the groups. Now we move on to a new concept, which is what? Which is electronegativity. En, which is what? Which is electronegativity. Electronegativity, it is what? It is the ability of an atom forming a covalent bond to attract itself not attract itself, to attract shared electrons to itself. Now, you don't need to memorize, but you really need to understand how the electronegativity is on the periodic table. Now, this is a very good example of how it's supposed to look like. Now, I'll just explain to you what is the definition of electronegativity in this sense. We have what? We have two atoms. For example, we have hydrogen. Let me find their values. Hold on. Here we go. Let's say we have hydrogen in combination with what? In combination with fluorine, right? Now, they have what? They have one covalent bond in where they share an electron. But this electron is not exactly in the middle. This electron goes more towards fluorine. Why? Because fluorine has a higher electronegativity, because it has a higher nuclear charge, first of all. So it has a higher tendency of bringing the electron closer to itself. And hydrogen only has one electron, so it's very hard for it to bring the electron to the other side. So this is the definition of what? Of electronegativity. Now you need to memorize these values. Of course, you don't take into consideration the noble gases. Why? Because noble gases do not lose or gain electrons. They're noble, they don't react. Okay, so they're not included. And we have what? We have a kind of rule that if we go across the period, the electronegativity increases. The only exception in this scenario is for hydrogen, yeah. Then if we go down the group, electronegativity decreases. So the only exception for this is the transition metal. So everything here, these are all exceptions, as well with these at the bottom. Okay, perfect. This is the electronegativity, basically explained. I didn't need to write too much. If you guys heard what I said in the picture, please do write whatever I said. Now, we reach what? We reach period 3. We have a whole couple lessons on what? On period 3, which I have no idea why, but it's important apparently. So what do we need to know? We need to know that as we go across period 3, meaning starting from Na all the way until argon, As we go across this period, the reactivity decreases, whether it's reacting with chlorine, with water, or with oxygen. Now here comes the most dreaded part of this chapter, which is the equations. Now honestly, it's not too bad, you just need to know how to deal with them. So if you have ionic equations, for example, let's start with the P3 reactions, the period 3 reactions. What did I write? R or P? What is this? P. Okay, so the period 3 reactions. First thing they will react with is O2 oxygen. Let's start with sodium. Sodium is plus, O is 2 minus. You do the crisscross method, you're supposed to get Na2O. That means Na solid, in addition to O2 gas, is going to give me what? Is going to give me Na2O. Now, what do we know? We need to balance it. Of course, to balance it, you put a 4 over here and a 2 over here. And we know that the color of the flame of Na is yellow. So I'm just going to put the yellow color over here. Next equation we have is Mg. Mg is 2 plus, O is 2 minus. Do the crisscross method, you will get MgO. So Mg solid plus O2 gas will give me what? Will give me MgO. How do you balance it? 2 here and 2 here. And it will give me what? It will give me a bright white flame. Because it's bright white, I cannot draw white on my white. So I'm just going to leave it plain. Okay? Perfect. Now for aluminum, aluminum is Al3 plus. And then O2 minus, you do the crisscross method, you are supposed to get Al2O3. So Al solid plus O2 gas will give me what? Will give me Al2O3, which is also a solid. It also has a white flame. You need to balance it. You put a 2 over here, a 3 over here, and a 4 over here. Now, for the rest, it's preferable to memorize them. So for silicon, it's a solid. In addition to O2, which is a gas, will give me what? Will give me SiO2, which is a gas. And what's the color of silicon? No, it does not have a flame. Then we move on to phosphorus. Phosphorus solid, in addition to oxygen gas, is supposed to give me P4O10, right, which is a solid. Now, to balance it, you put a 4 here and a 5 here. Now, what is the color of the flame? The color of this flame is what? Is yellow as well. And now, finally, last but not least, we have what we have. Sulfur solid, in addition to O2 gas, is supposed to give me what? Is supposed to give me SO2 gas. And another equation is 2SO2 gas will react with O2 gas to give me what? In equilibrium to give me 2SO3 gas. Now, what is the color of this flame? The color of this flame is blue. Perfect. Let's move on to, oh, by the way, what is remaining is chlorine and argon. Chlorine and argon do not react with oxygen gas under normal conditions. So they do not react, they are out of the equation under normal conditions. Now, the next equation we have is what is the period 3 reactions with chlorine, with Cl2. I'm not going to explain how to do it. You guys should know how to do it by now. I'm going to write just the finalized answers. So 2Na solid, in addition to Cl2 gas, will become 2NaCl. Now, the reactions are going to be decreasing as we go down the group. So you will see at some point we're going to have some liquids instead of solids. So this is what NaCl is aqueous if it's with water, but in general it's solid in this scenario. Solid. Now, Mg solid, in addition to Cl2 gas, will give me MgCl2, which is also what? Which is also a solid. Now, for aluminum, 2 aluminum solid, in addition to 3Cl2 gas, is going to give me Al2Cl6. This is supposed to be memorized, by the way, Al2Cl6, which is a solid. Now, silicon is a solid, in addition to 2Cl2 gas, right? It will give me what? It will give me SiCl4, which is what? Which is a liquid. Perfect. Then we have 2 phosphorus solid reacts with 5 chlorine gas to give me 2 PCl5, which is what? Which is a solid. Okay, and now finally we reach to what? We reach to sulfur. So sulfur solid can react with chlorine gas in order to give us what? In order to give us S. So SCl2, which is a gas, or it could be 2S, sulfur solid, reacts with Cl2, which is a gas, to give us what? To give us S2Cl2, and this is what? This is a liquid. Now, of course, chlorine is not going to react with itself. It's going to give us Cl2. That doesn't make sense. And then argon, which is a noble gas, does not react either. Now we reach the final equation, or the final thing, which is period 3 reactions with water. So let me just write them quickly. 2Na solid plus 2H2O liquid gives me 2NaOH, aqueous plus H2 gas, and then magnesium solid plus 2H2O liquid gives me MgOH2 aqueous in addition to H2 gas. Now there's another reaction. You could do Mg solid reacts with H2O as a gas, so steam, to give me what? To give me MgO solid in addition to hydrogen gas. Then after hydrogen we have aluminum. So 2 aluminum solid plus 3H2O liquid will give me what? Will give me Al2O3 solid plus 3H2 gas. And now last but not least, chlorine gas in addition to water will give me an equilibrium of what? Of HClO aqueous in addition to HCl, which is also aqueous. So perfect, that's pretty much it for all of this chapter. Thank you guys for watching. I hope you enjoyed and have a wonderful day. Let me just scroll up to the very top. Perfect. How much is 88 minus 65? Perfect, 23 pages. So thank you guys for watching. I hope you enjoyed and have a wonderful day.